and others online. So this is just a little bit about AI in medicine and why should we do that in CEU. So the thing is, what we are doing usually in CEU is critical appraisal of systematic reviews, evidence synthesis, RCT, cohort, case control, or expert opinion. And this is what is called evidence-based medicine. But if you look at what people are doing in the world now, it's all AI-based. The West seems to be moving towards AI-based precision medicine, like electronic medical records, wearable tech. Even in India, people have got smartphone linked to the doctor. So the arrhythmias are being picked up. I think one of our faculty, his father had SVT, and he had a wearable device. So even before he had a serious event, father got an alert, come to hospital immediately. So that tech is even there. So biosensors, nutrition, research data, images are now being looked, even in CMC X-rays are being read by AI. Literature review can be done for systematic review using AI. Real-time data. So all this together now is AI-based medicine. So much of things are there hidden. You can say the tip of the iceberg is what we are seeing. But below that, there's a lot of AI going on. So I thought I'd just take a little bit about what is AI. So today's class is a little bit only what is AI. Then every day, every Saturday, we do little bits of AI research. Today is only going to be a little bit about. So there's two things. One is the sources and uses. So healthcare data now is increasingly genomic data, medical images, medical records, environmental data, internet, social media, wearable devices, and phone. So actually, you can see that all this has now slowly become part of machine learning. Information from all this comes and tells you about health of a patient. So what is that machine learning? So we can use it for diagnosis. For diagnosing data, you put in all that information and you can tell the patient, oh, you have an arrhythmia, you're about to die. Now, previously, drug information, drug discovery used to take years and years. But now, if you look for COVID, there is virus structure. They have a huge database of potential molecules sitting somewhere else. And then they can just match it using AI, and the AI can predict the this potential molecule can work for this virus. And then we even said these are the ones that will be safe for human beings, and these are how much the effect you can expect. So it cut down drug discovery time from years and years into a few months. In fact, in a few days you can do that. So drug discovery. Medical imaging, I already told you about. We can put AI for X-ray imaging. Personalized medicine. Okay, both of you have COVID, but you'll decide, okay, Mercy doesn't need antivirals, but Sakshi needs antivirals based on personalized needs. Disease prediction is what many people use. That is, if you have a COVID patient, this guy needs admission because he's likely to get sick and die. Same, another old person is not likely to get sick and die, so he can be managed at home. So disease prediction. Smart health records. Now we have health records. So if you're screened OPD, for example, I'll show you a picture a little bit later on. Currently, we are sitting and typing EMR. And then if you have a little bit smarter EMR, we'll type diabetes, it will be married with the up-to-date, and the diabetic test to be done will be coming up. And we're ordering medicine and say these are the common medicines diabetes will have. Even smarter EMR is where you talk, when you're talking to the patient, it is recording what you're doing and immediately transcribing it into this stream. When you're doing the physical, you can talk into it as a physical data. Then it is learning from that, and I tell you, hey, Mercy, this diabetic patient, we forgot to ask these questions. Or this guy is from such and such a place where there's a lot of nephropathy. Why don't you ask him? So it is telling you how to take his screen. At the end of physical, it also telling you maybe you can ask these extra questions on physical. So it's adding to the electronic medical records and telling you that. Then after, so we'll come to that a bit. So then another area is coming increasingly into smart health records is also education. So now we have training videos, modules for students to learn. But then say, okay, Niven is a doctor, he's a post-MD, now he's 3 years, he's this level. So okay, Niven wants to learn something about nephrotics. The AI will generate a clinic for Anna has. And then when you start answering questions, it will keep giving you options and changing. So it's like a dynamic AI learning module, which is tailored for you. So, and then the information is good. So there are so many more things. So overall, you can say improving medical structures. So let's say X-ray, nobody really tests X-ray it seems. And then like half the findings are being missed by maybe younger doctors, junior doctors. So we can improve the existing medical structure by adding on AI to read X-rays. Upgrading medical structures. Okay, so now we have, let's say we're looking at pathology, just doing hundreds of malaria smears during malaria season. We can also add an AI which looks at all, first screens all the malaria smears. It will pick up everything which seems positive. The positives are read by a doctor. Independent medical structure. I was joking the other day, there's a physiotherapy hospital in Bangalore, but there are no doctors. You go tell you history and physical, the AI will tell you the diagnosis, and the nurses will implement the treatment based on that. So it's totally replacing a doctor in many situations. Where there's no lack of doctor, you go speak to the AI and describe history and physical, the AI will tell you what's required. So that's a complete change of the way in which medicine can be done. So that's called an independent medical structure where the AI has replaced the doctor. Okay, so this is another thing to learn. It's called the Gartner cycle. So what's the Gartner cycle? It's talking about AI. It's a bit of a tricky thing. If you look at innovation, okay, AI will replace radiology. For 10 years ago, I think 5 years ago, we all tried an AI project, and we got huge ideas, and it was a great innovation. Some of our own AI medicine people in Bangalore were doing this innovation of AI in radiology. Then suddenly you find that, oh, okay, much of the AI is false positive, meaning it's picking up every small dot and saying cancer and every other thing and saying this is TB. So there's a bit of disillusionment that, oh, AI is actually useless. Then you come a little bit of, okay, here is where AI actually can be useful. That's the slope of enlightenment. And finally, productivity, where everybody starts using AI. And after some time, you forget that you're using AI actually. So if you look at your smartphone now, you've got WhatsApp. There's a small thing on search bar called Meta. You can search your WhatsApp. You can also save it and search Meta. So you can put any medical topic you like or any topic in the world, and AI will tell you what a short summary of what you want. People are using it all the time and forgetting that it's actually AI. It's not Google search. It's an AI engine which is giving you an answer from searching the web. So that's where probably that Meta search is probably the plateau of productivity, where people use it without thinking that they're using an AI. So this particular cycle is called the Gartner's hype cycle. Okay, now I need to get out of the regular format. Where I need to get out of that. So now I'm going to tell you what is AI. Of course, if you know this is going to be a bit boring, but just bear with me. So what is artificial intelligence? There are methods for AI and there are applications for AI. People commonly like call everything as AI. You must know there are two separate things. One is the technology you use, and then the second is the application. So the tech you use could be things like evolutionary computing, experts. You see sometimes of your lap or washing machine uses fuzzy logic. It will decide what kind of clothes you have. It will decide what type of dirt level is there and how much volume is there, and it will decide how to clean the. So I'm saying that's what's called fuzzy logic, where it can use its own thinking. Then there's something called machine learning, which comes under the method. In machine learning, there are many types. I'm going to talk about those types. One of them, for example, is neural network, which sort of imitates the neuron of the brain. And there's another called support vector machine. There are many types of machine learning. There's another thing called probabilistic methods. One is called Bayesian networks. Bayesian is you're using prior information married with the current information to come to new knowledge, which is called posterior knowledge. You can use that also in AI. Markov models are sort of prediction models, what's likely to happen in the future. Then the application of these methods, there are many kinds of them. Natural language processing, now Google Translate, you can look at so many material and so that's called natural language processing. Information extracting, translation. Planning and scheduling, so many of the airports use AI, plan people's travel trips, all those AI engines or even the travel engines will tell you based on your age, gender, your likes, dislikes, when you want to travel, it will sort of make a schedule for you. So the AI engine can do that. Predictive analytics is what many people want to do, like, okay, what's the chance of Sakshi developing diabetic in for 20 years? So therefore, that she has to change her lifestyle like this. Predictive analytics. Vision, image recognition, machine vision, image recognition, for example, now this Neuralink, Elon Musk technology company. For blind people, the next, so now right now they put, or quadriplegic people, they put a sensor into the motor cortex. It reads when he wants to move his hand or do something. He's quadriplegic, but he's able to, the computer is able to do what he wants to do. Can't make him move his hand here. Now they're going to take people who are blind and put the sensor into the optical cortex, and then they'll have a camera in front of the eyes like the spectacles. So that camera will record the vision and the vision will be transferred to the optical cortex. So they'll be able to see an image, not 100% clearly, but some sort of an image that we are able to see. So that's the next thing about vision. Then there's robotic speech, speech to text, text to speech. These are all the applications. There are thousands of applications. But just remember that when people say AI, machine learning is one type of method of it. But people use the word interchangeably, like machine learning and AI. AI is a big thing, but this classification also many people don't agree. But this is one particular classification which seems to be good. So then I'm going to teach some more about this. Machine learning itself, that is this one, machine learning. There are two types or three types: supervised, unsupervised, and reinforcement. So now we're slowly getting to the new terms, or you heard it earlier that there's something new to learn. That machine learning, that is this one, method, can be three: supervised, unsupervised, and reinforcement. And I'll teach what these three things are, but it's something new to learn. The next thing to understand is that this is 1900, this is 2020, or you can say 2024. This is our average human being. Let us say you decide to anesthesize a diabetic patient or a hypertensive. By the time she decides which antihypertensive, she's thought of 5 facts, mostly up to 5 facts: age, gender, comorbidities, other illnesses, and cost. So these 5 facts probably will make Anna decide this antihypertensive. But Vignesh may see the same patient, give a different one. But the important thing is that human being can usually process 5 facts for every decision, maximum 5 facts. So that's that. Now, that's clinical phenotype. I told you, age, gender, 50-year-old man with obesity and diabetes, previous MI, and poor man. So I'll give him beta atenolol instead of cilnidipine or something. But then suddenly when you start giving the person genotype evidence, then I also give this analysis in gene structure. Then suddenly you're going to need about 10 facts to make a decision. If I give you gene profiles and functional genetics, it becomes 100. If I give you the patient proteomics and genomics and all the omics new data, suddenly it becomes beyond what the human brain can comprehend. So with the increasing amount of information available to us, it becomes information overload. Sitting in the OPD, like, what am I going to do with all this information? So we'll land up going back to the 5 clinical data that we are going to use. So machine learning is really useful because it can process all this huge amount of information and give it to us in a usable form. Give, don't give. Dr. Vignesh, this patient give beta blocker, but instead of atenolol, give metoprolol. something like that. So I'm just saying, so this is also called this information cognitive capacity and what actual information that we are started getting by this machine learning. Now I told this long ago once before. Let us say that this is the height of a patient and this is the weight or age of a patient and this is the height. And let us say that, for example, a child, as the age grows up, the height should go up like that. Okay. So then, what is the whole goal of predictive analytics? I want to be able to predict. So we make a usual equation. If you remember the equation, I don't know if you can write on the screen. Y is equal to, oops, I can't write on the screen. So we'll make an equation. Y is this one is equal to something times x. X is the slope of the line. So that's how we make an equation. Now you can see that this is called underfitting of a line because the line is here, but some dots are above and some dots are below. So this line is not really a representative line. It's called an underfitted equation. So your equation did not really fit the data. Then there's something called overfitted line. Imagine that you trace every single dot. So you can make it as a quadratic equation and more sign equation, all those kinds of mathematical jugglery one can do. Y is equal to something, and you can accurately trace out every single dot. You'll be very happy. But remember, when you're doing this prediction, you take one table, let's say Anna's thesis is there. And Anna says, my Y is equal to this. I can predict every dot. Now, Anna, the future Anna collects more data and sees how well her previous model worked on the new model. Will it work well? It won't work well because you cannot practically get all the same dots back again. But your equation is meant for this kind of a straight squiggle. So it's called an overfitted model. So you should not try to chase every single dot when you're making a prediction. This is not chasing any dot at all. So neither should you underfit your model, neither should you overfit your model. Okay, these are the dots I got. I made a line like this. This is probably a balanced model of data. So when one is making this machine learning, or even this is here for logistic regression, linear regression, you should always ask the statistician, please get me a balanced one. I don't want it to be overfitted, neither do I want to be underfitted. This is underfitted when I don't match all the dots at all. When you match every single dot is overfitted. This is a balanced model. So when you're looking at something called high bias, bias means it's not able to pick up anything. It's not able to fit the data at all. When you have low bias, as you become more and more expert in doing this prediction, your bias becomes less. Low variance means the data is all similar. When you're doing a small study, the data is similar. But if you look at large volume, whole of CMC data, whole of India's hypertension, diabetes data, then the variance becomes very high. So you can underfit the data or you can try to do less of overfit. So what is the testing data set and training data set? Testing set is Anna did a study and she developed a logistic regression model. That's testing. Training data set is Anna does another study and tries to see how well her model, which she developed in the first version, works on the new set of patients. That's called the training data set. So as you go on towards the right side or towards my left, the complexity becomes more and more. So that's another thing to keep in mind. Now, Dr. John does a study and says, look, I can't do another study after this. So what do? You take 70% of the first study data and you train your model. Just take any one of your thesis and you take only you divide SPSS will randomly divide 70% and 30%. You don't look at that 30% first. You develop a logistic regression or a linear regression on the first set. Then you say that's my training set. And then you'll apply that on your new set, which is remaining 30%, and call that your testing set. And then you say, yes, I have verified my model. I validated my model. It's not exactly correct because that 30% is from the same group of patients where 70 came from. So it will very likely work very well. But imagine if it doesn't work well on that 30%. So I have a problem. Then I must try to tweak it, and then I must take it on a fresh set of people. That's actually when one validates a model. So these things become important when one is, so the training and testing So underfitting is usually a high big problem always. Overfitting tends to be low in the initial part, it becomes high after that. And balancing of the data is generally low. The balanced version. Okay. Now there's something called black box, which you often hear the word black box when one does machine learning. What is black box? If you look at, let us say, all you guys have done linear regression, logistic regression for your thesis. You guys did, but you all have done some. So might have done. So linear regression, logistic regression is on this side. It's easy to interpret. Interpretation is easy. So a simple model, linear regression, common statistical techniques, which we all understand. Or all simple laptop can do that. As we come to machine learning on this side of the equation, this neural network, support vector machine, this becomes more complex. Here we're looking at linear relationship. I told you the graph, as x increases, y increases also. Slowly in machine learning, it becomes non-linear. You can't predict how can Mercy get diabetes, whereas Sakshi won't get both same age, gender, everything same. But one determines this and this. So it's not a linear, it's a non-linear equation. The statistics done in machine learning, we can't understand it. It's quite complicated and nobody can understand it. Lastly, you can't do a normal simple computer. You need a computer with a 10 terabyte information and the RAM should be 100 RAM or 200 RAM to even start doing machine learning. So after some time, this becomes called a black box because nobody can understand what happens. I put whole of CMC's data and suddenly this Niven is not going to get diabetes and so on. How did it come to that conclusion? We don't know, but it says with 90% accuracy, Niven will never develop diabetes. We don't understand what it did inside. It did something and came up with this prediction. That's why it's called a black box. Okay, so this is called supervised learning. You have a problem definition. What is the chance of PGs in medicine getting diabetes in the next 10 years? You take a data set, we have all the data available for medicine PGs for the last 10 years. The day they joined CMC, and they all stayed in CMC for 10 years after MD, also they finished and stayed for 10 years. We have the complete data set. We pre-process it, we get rid of all the useless information, there'll be some address and something else. Then we develop a machine learning model, and we see how well it predicted diabetes, not diabetes. So this is called a supervised learning because the data set is completely labeled. That's what's called supervised learning. That means all of your PG thesis was completely supervised, meaning on age, age. Then the next one, MS, you put gender on top. Next one, HT was height. So everybody, the computer knows what is HT and what the values mean. Maybe Mercy might have coded 1 and 2 for gender. But somewhere that code is given, 1 is male, 2 is female. Or 1 is diabetes, 2 is non-diabetic. So that's what's called supervised learning, is where the predictor variable and what is being predicted are completely labeled. It's called supervised learning. So let's see what happens in supervised learning. Everything is labeled. Feature selection is what, let us say, firstly, what predicts diabetes? Family history, diet, lifestyle, drugs. Those which we call variables in machine learning is not called variable, that's what we introduce a new term. Those are called features. Because machine learning came from engineering and from computer guys. We did statistics, so we call it a variable, a predicted variable, independent risk factor. So we got to get used to the words they use because increasingly they are coming into medicine. Or we can say now we are slowly entering the world of machine learning, artificial intelligence. So we learn to talk the same languages. So the word feature selection is what are the variables you're going to include. So imagine in a data set, you could have thousands of data per human being. We are only using general medicine, age, gender, few. But a human being will have thousands of things to describe it, where they are from, blah, blah. How do you choose among those variables which features you want? There are thousands of variables which I can use to predict logistic regression. How do I select those which I want? That technique in machine learning is called feature selection. There are too many variables. I want to narrow it down to few variables. And then I have some features. Then I do a logistic regression, linear regression, machine learning. This is step one. We can, no, that's where, so we can tell the computer some and it can choose by itself. So there's different methods of doing that, partially helping the doctor or completely done by computer also is possible. So this is the training set. Then there's a validation set where I divided 70 and 30. So in this 30% which I am trying out now, again I have a label, I have a testing data set, the 30% feature selection, and I am going to see. So this is where the machine learning is predicting now. Okay, I'm able to predict on my new set with so much sensitivity, specificity, I can detect this disease or whatever. Then the last step is using the data. Now we are employing it in medicine OPD. Patients come and the doctor is sitting there and a pop-up comes and asks something. This guy is likely to develop that. We don't ask all these things. The new data, this is a new patient. And the computer is, the machine learning is having a feature selection. It chooses the, it chooses the features and gives the output. Prediction. This guy is getting that. So this is how machine learning is supervised learning happens. Okay, this is unsupervised learning. This is the raw data. As you can see, the raw data has no meaning. To the computer, it is not told that this is a moon, this is a star, this is a polygon, this is a hexagon. It is just given some data. And it says, show us some patterns. What is going on? What's the underlying story? You don't know what the computer does, but it has taken the moon, the stars, and the various other shapes and classified it. The computer is capable of doing this. So, in this is also called pattern recognition. Sometimes when you don't have a gold standard diagnostic test, you know what that's called? What test one can do? You can, it's an artificial gold standards will be created. How is that artificial gold standard be created? By looking at patterns and trying to put people in different bunches like that. So in a sense, this is a sort of pattern recognition. So unsupervised learning will look like this. You just give the computer a mountain of data. Google looks at a mountain of data. Nothing is, the information captured by Google is not labeled. Oh, this is Anna, this is her gender, this is her age, this is it captures a large amount of data and is trying to get some pattern out of it. Oh, you're likely to want to buy shoes from X company because you seem to be in this box. So I'll show you this ad. Totally unsupervised. Okay. So now let's look at some names again. Remember that we put serial number when we collect data for our thesis, serial number 1, 2, 3. They call it instance number in machine learning. We have hospital number, but they call it sample ID, whatever the ID in that study. These are the features, the thickness, the cell size, cell shape, adhesion, epithelial size. These are all called features, and we would have called this risk factors or variables. Outcome is, we call it outcome variable or independent variable or dependent variable. They call it class. They don't say outcome variable, they call it as a class variable. This is something to learn. When the machine learning people say what class it is, class is basically the outcome variable. Feature is predictor variable. And instance is the serial number, and sample ID is the hospital number or whatever you use to vary in that particular data set, how it is captured. Next one. Have you seen this before? Where is this? Which study design? Diagnostic study design. In machine learning, this is called confusion matrix. So we'll come to that next time's class a little bit more in detail. The same thing, but just remember that the predicted outcome is here. In diagnostic study, we have gold standard and new test, and therefore we are used to that false positive, false negative, true positive, true negative, that's best. But here it is actual outcome. Let us say that I have a large data set of medicine PGs, and an actual outcome in 10 years whether they develop diabetes or not. And this is the predicted outcome. So that's how this predicted outcome is negative, actual outcome negative, true negative, predicted outcome positive, and they develop diabetes, true positive. They predicted diabetes, but the person didn't get, so false positive and then false negative. So this is now a machine learning called the confusion matrix. So just get used to the new terms in this. So this is an example of a confusion matrix I've taken from a paper. So you can see that this is a different types of machine learning models. Generalized linear model, support vector machine, artificial neural network. This is the predicted outcome. Let us just take one, generalized linear or support vector machine. In predicted benign and malignant as 0 and 1 or outcome. What did they call it? Class. So their class. And the actual outcome was benign malignant, and you can make a 2 by 2 table here for support vector machine. The sensitivity of the support vector machine was 97%. Specificity is 94%. Accuracy is the total number of true positive and true negative divided by the overall. Accuracy is 96%. So this is how a confusion matrix is presented in machine learning. Same kind of words, but you just have to get used to different kind of terminology, and the 2 by 2 table is slightly different.
So this different methods there are. So this these three methods based on the study design.
Yeah, we'll come to that. So when you use what, I'm going to teach next. That's a good question. So your question is when to use what? We'll tell you that. Now you remember this from PG days, ROC curve. So that luckily they also call it as a ROC curve. So we're lucky that they also call and generalized linear model, support vector machine, and neural network. So you can see that each of these has got an area under the curve, and the best one appears to be support vector machine in this particular story. The previous one from this predicting benign and malignant, you can say that because the area under the curve for the support vector machine is better, it seems to be a better. For the same, they also use ROC curves. We also use ROC. So, how are you doing time? First one, maybe another 5 minutes. So, okay. So then we have something to learn. You ask the question, what about this large volume of data? How is it being processed? So there is something called data cleaning methods. Data cleaning is, there is a lot of missing data. What are we going to do for that? Or the data is wrong. Somebody instead of putting height in kilogram, put height in gram, or somebody put in milligram, which all looks quite different. Data cleaning. Data reduction method is we've got thousands of predictor variables. We want to reduce them to a manageable 10. That is data reduction. We are not trying to chuck off the data, but for our model, we clearly can't put 1,000 variables in the model. How do we reduce it? Types of learning methods to be supervised, semi-supervised, and reinforcement, unsupervised. Unsupervised, I told you there's no labeling of male, female, outcome variable, or class variable, or feature variable. Supervised is completely done. Semi-supervised, can somebody give me an example? I think I told the story long ago in the movie. In World War II, how did they predict? You know the movie? What's the name of it? Who cracked the code? The father of AI, Alan Turing. So he found out the German code because he knew. What did he know? What word did he know? Every day they changed the code. So they were bombing ships in US, UK ships, but they could not figure out how the Germans were communicating. Every day they changed their code. So what? So Hail Hitler or Heil Hitler was the code which remained. That was the last sentence of every German message. So he used that. I know that H is this, E is this, but only few. But with what he knew a little bit, he could figure out the rest. So some of the data was labeled, some of the data was unlabeled. That is called semi-supervised learning. So Google is always trying to use it as semi-supervised. Give your feedback. Can you give some data? Where is it got some data from you? Semi-supervised learning. You can take something of what you do and do. Then there's what is called reinforcement learning. Reinforcement learning is like a Pavlovian experiment.
Every time the dog does this, it gets a whack. If it does this, it gets a reward. Reinforcement learning is a whack for the computer. Hey, you predicted wrong. So you do a thesis. My model didn't work. Okay, none of the variables which I used predicted the outcome. Too bad. So that nobody publish your data or people say, what is this learning? But machine learning has a feature called reinforcement learning. Okay, predicted wrong. Go back, change the variables. Now you see your prediction. Slightly better. Go back. So this is an iterative process. So machine learning is reinforced learning because it can keep on doing millions of times. There's no limit to the number of times it can learn till it comes to a good enough answer. So there's an important principle of machine learning is called reinforcement learning.
Unsupervised learning. You have to ask for an outcome or does it just randomly?
So it randomly gives you things. And then you will have thousands of associations. Like when the crows fly over Vellore, it will be earthquake. That's totally nonsense. I'm looking at the health outcomes of people in Vellore. So you will have to filter through lots of associations. And then, because there's no question asked of it. You just show me in this large data set various any association you find. Then it's not meaningful. Can also turn out that a specific data set to sort of try and say something. So that's the problem with that. Simulation-based evaluation is there's no data. It will simulate the data itself and tell you what will happen. And I'll show you in the next classes how it can do that. There's no data at all, it can tell you what is likely to happen. Practical implementation-based evaluation has got data from what has happened, and using that it can tell you what is likely to happen. Applications currently mentioned mostly for diagnosis, treatment, and for their prognosis as well. So these are the applications. Okay. Now, data pre-processing. So data cleaning schemes, I told you, we have got a lot of thesis data. And if you ask a statistician, what are you doing? Why you take 1 month to analyze my data? Doctor, I'm cleaning your data. What is cleaning the data? Missing values. So the computer has many methods of filling up missing values. And we can put past observation carried forward, baseline observation, and more baseline observation carried forward. So many techniques are there. So that is that. Managing noisy data. Noisy data is like somebody put milligram, somebody put gram, somebody put kilogram. The computer will decide, okay, I'm going to convert everything to kilogram and put it there so that the data becomes less noisy. And data normalization. Hey, this value is completely skewed. That means for ease of analysis, let me normalize the data. Either I can make it into normal or I can log transform the data. So many things will be going on in the background. That's called data normalization. So data reduction scheme, I've got now 1,000 variables which are cleaned and ready. Okay, feature selection. Okay, I'm going to choose these features and I'm going to extract those features and use it for my logistic regression, linear regression. That comes under data reduction scheme. So, unlabeled data set, unsupervised learning. Yeah? Labeled data set, supervised learning. Labeled and unlabeled data set, semi-supervised learning. Wrong diagnosis, reward. Go back, action, reinforcement learning. You keep on trying till you get the correct answer. So these are the different types of learning in machine learning. Yeah, supervised, semi-supervised, unsupervised, and reinforcement learning. This is just an example. Now you have a patient, they come to you, you take blood. TME stands for tumor microenvironment. So it's got a data, the computer gets all the data. Clinical, genomics, structural genetics, epigenetics is how the environment modifies your gene. Transcriptomics, proteomics, metabolomics. So you can get everything from a single blood test now. We'll give you all that information. Then it starts pre-processing, normalizing the data, categorizing the outcome, what is the outcome, each variable, batch removal, outlier removal, then feature extraction. What are the features I'm going to take to predict whether this person has got cancer or will do well or badly? There are various methods, machine learning methods to do that. Then the model LR is likelihood ratio. Because the outcome is yes or no. So the one important thing when all of you do the paper on machine learning, Have they reported logistic regression, linear regression? So that's what we are used to. At the end of the model, they should tell you that all my fancy machine learning has it been better than machine learning or logistic regression. Dr. Vignesh did a study of 1,800 sepsis patients, and we had about 300, 500 variables per patient. So Dr. Jayasinghan had a lot of machine learning as well as logistic regression. At the end of it, the support vector machine, I think, was slightly better than logistic regression. So we didn't become very clever. It's not clever. We're wetting our hands into machine learning. But the logistic regression was fairly good. Even though people say logistic regression, linear regression, if you have data set of 1,000 human beings, 1,000 variables per patient, all these will not work. They still tend to work reasonably well. So what method you use and the final output. What could the output be? Classification. You will respond to chemo, you will not respond to chemo. Risk prediction. You will die, you will not die. Progression-free survival, recurrence classification, people can deal with that. So this, what does it get inside? It can look at the cancer cell type, human. So there are different data to get from whatever information you collect. The machine learning takes all this information together and takes all this information and finally gives you an output. So this is a sort of a wide summary of what happens in the, for example, so this is an example using tumor micro environment. Okay, I'll stop with this next few slides. You asked what are the supervised learning and where to use them. That was Anna's question. So Anna, I'm just telling them that if you take blood from somebody, you can predict their response to cancer, survival, progression-free survival, recurrence, using just mountains of information that the computer calculates and it processes it through and gives you a prediction at the end of it. So this is increasingly being used in many places. So let's learn this. Some more, a lot of new words today, but it's good to learn. Remember supervised learning? What's supervised learning? Everything is labeled. Features and the what is the output for? Class are all labeled. So these are the words you get used to when people talk about supervised learning. Naive Bayes. Maybe we'll teach a little bit about naive Bayes next time. So nice Bayes we all know, pre-test, poster probability. Decision tree, artificial neural networks, ensemble we put all together, random forest, deep learning, support vector machine, and K nearest neighbor. These are all methods from mathematics and engineering and computer science which are coming into this. These are called supervised learning. And this is too much information, but I'll give the slides to everybody now speak on. It gives the advantages and disadvantages of each of these particular types of methods. I'll just take one example. For diagnosing chronic kidney disease, the machine learning technique was K nearest neighbor. And it could diagnose with an accuracy of 99% a patient with this person get chronic kidney disease. So this is an example of supervised learning. So now you got used to this. So hidden here, K nearest neighbor is KNN. So that there are different types. SVM is, let me see, you get used to the word support vector machine. So just get used to this SVM, K nearest neighbor, random forest, artificial neural network, naive Bayes. These are the words that people are increasingly using. So these are the examples of supervised learning. Any questions on this one? And this is the example I gave you, K nearest neighbor for diagnosing CKD. Unsupervised learning, again, K means clustering. Plus K nearest neighbor, this is K means clustering. So slightly different. Artificial neural network comes here. Fuzzy C means, so fuzzy logic comes as a unsupervised learning. Hierarchical clustering. So these are the words you get for unsupervised learning. And this slide I'm not going to go through right now. I'll share the slides. These are the slides for the advantages and disadvantages of each of these particular methods. So let's just take an example. Retinal examination, fundus. And it's going to look at diabetic retinopathy. So this is an example of unsupervised. You can just put it inside and it can diagnose up to accuracy of 99%. You just put the funnel and you just pencil whatever. It is not taught anything. You can use one example of segmentation of retinal fundus imaging. The last one, reinforcement learning. Reinforcement, I told you, keeps learning back again and again. The names you must get used to is called the Monte Carlo methods. It is there in statistics. Monte Carlo, MC methods, Markov chain, Monte Carlo. Just Google that. It's a nice concept to read. Increasingly, people are using that. And there's so many other ones: deep reinforcement learning, dynamic programming. And there's some advantages and disadvantages which you don't have to go through if you're interested to learn. There's a nice example for using this. COVID-19, predicting COVID-19 pandemic, and they use some of it and they learn. I think I missed that slide. This is reinforcement learning. I missed the slide here. No, that's correct. It's reinforcement learning. Yeah, they use reinforcement method. Okay. What's the time? 12:30? 12:30. Okay, maybe this is the last slide since I put it on. If you remember that 1950 when they sent a man to the moon, that was the supercomputer of the time, and it had 5 MB megabyte space, and it was considered phenomenal, and that was called the Ramak computer, and it was a whole room full of computers. Then came supercomputer in 1985 when all these Apple and all those fellows, Steve Jobs, and we thought they were the coolest chaps on earth. And they had a computer which looked as big as Steve Jobs, 32 GB from 5 MB, 32 GB sounded like a phenomenal amount of space. Now this is taken from 2018. And in 2018, the iPhone XS had 512 GB, and people thought that was an amazing thing. But just look at the size and the amount of storage. As time went on, the storage has become more. And this is in processing speed, millions per second. And you can see now in 2020, an average computer can make 1 million calculations per second. Whereas in 1970, it was doing like 0.1 million calculations per second. So artificial intelligence in medicine also has to keep up with not only increasing storage space, but also the ability of a computer to do that. So we'll go to this article if interested. There's a New England Journal of Medicine article on AI in medicine, users and not users. So it's a nice article to read, so that we can stop here today. And tomorrow, next Saturday, we'll continue on this slide. So, any questions? That's all. Okay, maybe it's good to tell the harms of AI. This is a fundus photo, and medicine tool. I bought a fundal photo machine, and the model initially says healthy. It's remember that in medicine, in research, actually we're not saying yes or no. It's always probability. And why is the probability of disease, not the absolute certainty of disease. So the AI says this is most likely there is 90% chance that it's a healthy fundus. There is, let us say, 10% chance it's an unhealthy fundus. But AI has some pitfalls as well. It not only looks at the fundus, it looks at all sorts of noise. All sorts of information is put into the AI. That's called noise. At the end of it, if you look at this image looks the same as this, right? There's no difference in the image. But the AI has now said with 100% certainty or probability that this is diabetic retinopathy. So it's made a mistake. So AI can make terrible mistakes as well. So the fundus of the healthy retina is taken here. Correctly diagnosed, normal. In the middle, noise is there. That's because noise is everywhere. What is noise? Everything is not useful for prediction. And because AI is using thousands of data points, not just few that we use in medicine, that's all called the noise. On the right, we can't see that this noise is superimposed on the image. That image and this image look exactly the same to human eye. But for the AI, it is seeing that noise mixed with this. And then it's starting to predict, oh, this is diabetic retinopathy. So we need to be a bit careful about doing this AI mix. It can lead us to wrong diagnosis. Not because the computer made a mistake, but because it's taking all this information which is actually noise for it, and it makes up something bad. That's really just a sobering thought before we move on to the next. Oh, thanks, guys. So we'll meet next Saturday. I can give Sakshi a hand. Oh, well done. Good question. Oh, any questions? No questions. So, yeah, no, the noise is, see, like, if you look at, if you check sample size, suppose you're doing the height of the patient is out there. You're asking what is the noise? Noise means how much does it vary? The mean height then will be average height of all of us are calculating sample size. What is the expected mean? 150 centimeters. Standard deviation is the variation around it. So in the sense that is the noise, how much it varies. In research, other than what you want to predict, everything has become noise. So this is the age of the patient, maybe noise, maybe that's not useful in predicting retinopathy, where they are from, their smoking, diabetes, alcohol history, all the other information which is not useful to predict the outcome is now called, because it is distracting away from the ability to that. And because now we are taking thousands of data points and trying to predict an outcome, all those are noise. So that becomes.
How do they ever know whether it's been?
So this is the first time the computer does it. So this is the validation. This is not this is development now. Then we must validate it on the 30% with data which is kept separately. Then we must validate it on a new set of patients from the same place. The developed in Shell Hospital by a PG, 70% it did correctly, but when it did another 30% it made mistake. Reinforcement. Go back and make sure it does it correctly. Then in Shell Hospital, you redo the same thing. In Shell Hospital, on a new batch of patients, it is exactly doing this as compared to a ophthalmologist. Trained ophthalmologist is the gold standard. Then you take it to Chennai, to Bangalore, to US, to Germany, and see in a different situation, can you validate it? Then you say it's a valid model. So look at that machine that we are getting, the MLU. Before we got it, the first question is who's validating it? Shell Hospital uses this MLU device. They published from 6 other places in India that this machine now independently you just go to any OPD patient and the AI will reasonably accurately tell you diabetic retinopathy or not. Having said that, there's another problem. Then in Shell Hospital, when they say DR, the ophthalmologist will recheck. What's happening? Reinforcement. When you make a mistake, you tell the computer that error. You give a feedback box. So did I correctly diagnose? No, you made a mistake. In fact, you're helping it to do a reinforcement. So every time on Google, are you happy with the page? No, hey, it's reinforcement. Okay, something went wrong. What went wrong? Can you share what exactly went wrong? The computer is doing reinforcement wrong. But the problem for that is what we have found on medicine is for that reinforcement learning is on their computer in a cloud on a server. So our images of our retina has to be shared with that company, and our private patients' information will be shared on the cloud somewhere. They can use that information for teaching purpose somewhere. They may share that information with somebody else. So patient privacy becomes an issue. So the last lecture set of this will be AI. Like, would you be happy if your fundal photo is shared with somebody? Yeah, what is their funders? I can't be about this chancing one. No, but still, why should my funders photo be shared with somebody? But if you're not careful, your funders photo will be shared with everybody. And some IRB somewhere say, no, this is no ethical issue, share it. So AI ethics has become a research ethics has become a huge deal. Because so many patients' information is being collected without their knowledge. The government says, yes, we can calculate, we can collect all this and we can do that. It's an important thing. If you go to China, you'll find there are not many policemen. You know why? There are cameras everywhere. Their facial recognition technology. Then they can look at the AI will predict based on your face, your friends, what they're searching, and whether you have done any militant activity, whether you are likely to be a threat to the society or not. That's good. And in fact, in China, they're classified people as highly loyal to state. Then you get extra house, you get extra car, your children get free education, best universities, etc. So if you're other end, you get a thing. With facial recognition technology, without your knowledge, they're capturing your image and they're doing all these things. So it has a huge impact. Sometimes they kill some people. You find that suddenly the wrong person was shot. This is about 5 years ago. They caught somebody in UK in the station, and then they put a gun at him and he ran. They shot him and said he's a terrorist. It turned out the facial recognition made a mistake. They identified him as somebody else who was a terrorist. And he ran because if you put a gun at you, won't you run? Because then you're guilty, you're running. So it can make terrible mistakes on something. Technology has a big side. Thank you, sir.